I will start with a quite lengthy physical motivation, and then explain some mathematical results, which hopefully, I mean, you hopefully will see that they are somewhat related to this motivation, and I will not give any proofs. So I'm a mathematical physicist, but I will start now with a physics introduction. And the motivation for what I'm going to talk about, I mean, I will explain what I mean by bulk gap interacting systems, but you will very soon see what I mean. So the type of system I would like to, we would like to understand better are actually, quantum Hall systems. And I'm sure that you all have seen this slide too many times, because actually in mathematical physics talks about the quantum Hall effect, it often appears as the first slide as a motivation, and then people do something abstract about bulk and edge indices and topological quantities and stuff like this. So actually I never used this slide yet, but now I only learned a few years ago that actually the picture I had, and I think the picture that is conveyed by many mathematical physics talk about the quantum Hall effect, is not really the full picture. And as a motivation for what is going to come, I would briefly recall to many of you probably, and maybe to some of you it's also new, how the physicists who are really doing these experiments, and they're the theoreticians computing really, for example, current distributions in Hall bars, view the quantum Hall effect. So the pictures are all taken from physics papers, and here I write the papers I took them from. So of course the quantum Hall effect was discovered much earlier by von Klitzing, end of the 80s. But these are the papers I took the pictures from. So the setup is a so-called quantum or a Hall bar depicted here. So we have a two-dimensional electron system or electron gas. How this is created is not so important. It's at the interface between two semiconductors, and then there's some doping involved to fill this interface with an electron gas. But important is that we have a 2D electron gas and a magnetic field perpendicular to this plane. And then the Hall effect just says that if you, for example, drive a current through the Hall bar, then there will be a Hall voltage across the bar. So current along the bar will create a Hall voltage across the bar and vice versa. And the quantum Hall effect is the observation that at very low temperatures, the ratio between the Hall voltage across the bar and the Hall current along the bar is not linear, as would be predicted by classical electron theory and Ohm's law, but that you see these steps, and the inverse of this Hall resistance, the Hall conductance, is actually quantized in integer multiples I of a universal constant. Okay, that's the experimental setup. And I would like to say a few words now about how to understand this behavior in actual finite width Hall bars. And here I took some pictures from a paper by O and Gerhards. Gerhards was in the von Klitzing group. They worked a lot together. So how they describe it, they have the following picture. Namely, and what is plotted here is on the left-hand side, it's a cross-section of the Hall bar. So basically here along this direction, we cut the Hall bar. And we assume that at least here in the center, it's more or less translation invariant. So we only have this cross-section here. And here it's plotted the electron density at equilibrium. So no Hall current yet and no Hall voltage. And the electron density is computed using Thomas Fermi approximation, or Thomas Fermi theory, or more precisely, magnetic Thomas Fermi theory. So what you see here is a depletion area at the edges, and then this electron density in the middle of the bar. And on the right-hand side, you see the corresponding potential, self-consistent potential, which is the sum. So here also the solid line, which is the sum of the external potential, if you like, created by the doping, that, so to say, that confines the electron gas to this strip or to this bar. But in addition, also the electrostatic potential generated by the electron density itself. And what you see is that here, in the center, this potential is constant, meaning there's no electric field, and that's because of screening. The electrons move in such a way to screen the external applied potential. And this is possible because actually here we are in a situation where we have a very large magnetic field, and the chemical potential mu is exactly at one of the or at the lowest Landau level. So these dotted lines actually are the Landau levels, and if the magnetic field is sufficiently large, the chemical potential is at a Landau level. We have actually a partially filled Landau level, meaning the electrons can move around and screen the external potential. So if one decreases now the magnetic field, meaning that the distance between the Landau level decreases, but also the density of electrons that fits in a Landau level decreases, suddenly there will be a region in the center here of the bar where the first Landau level is now completely filled. And only at the boundaries here, there will be regions where the first Landau level is partially filled. And in this region where we have a completely filled Landau level, what the physicists call incompressible electron gas, it's not possible anymore for the electrons to move around and to screen the potential. So in this region, we will have again a non-constant potential. And now if one decreases the magnetic field even more, eventually electrons will be able to partially occupy the second Landau level. And so to say, in the middle here on this plateau, a new dome will form where the second Landau level is partially filled. And this constant region will move to the edges. Okay, so this is just an observation about how the electrons behave in such a Hall bar in equilibrium before a current or a voltage is applied. And actually, that this is the correct picture was, at least in the usual semi-classical limit, actually proven in a paper by Elliot Lieb, Jan-Philipp Solovey, and Jakob Ingvarsson. However, they consider so-called 2D quantum dots in magnetic fields. So now you have a confining potential only in one direction, but really a harmonic trap, if you like. And they showed that you see exactly this behavior predicted by this magnetic Thomas Fermi theory in such quantum dots. So the same behavior, if you have only a partially filled lowest Landau level, then you decrease the magnetic field, you will see that you have regions where it's completely filled. And then you decrease further, then you will have regions where you completely fill different number of Landau levels. Okay, surprisingly, actually they don't make any reference to these Hall bars, to these computations of physicists in Hall bars. And also the physicists don't make any reference to these papers. So that I found surprising. Anyway, now how does this observation about the electron density give at least the first step in an explanation of the quantum Hall effect? So this is again the same picture, cross-section of the Hall bar. Now from a different paper and graphically a bit different, but the idea is the same. Here we are in equilibrium. We have regions where some Landau levels are partially filled. These are the gray regions up here, and regions where there are only completely filled Landau levels. These are the white regions up there. And these white stripes is what physicists call incompressible stripes in these systems. And these are actually the regions where the electrochemical potential can change, because in the regions where we have partially filled levels, we have screening. Okay, and then the idea is if you now apply a Hall voltage, so actually even at equilibrium, since the electrochemical potential is changing in these incompressible regions, you expect to have Hall currents flowing in these stripes. However, they will be by symmetry cancel each other, so you will have no net current. And I would also like to emphasize that at least in the non-interacting picture, it's completely, or it's very well understood that if you have such regions where you have completely filled Landau levels, and in these regions gradient of some electrochemical potential, then this will lead to a quantized Hall current. So a current which with a quantized conductivity. So basically, explaining the quantization of current in these incompressible strips or stripes is it can be done along the usual arguments that at least my colleagues from mathematical physics know about, what people usually do for quantization of bulk conductivity. Okay, so the quantization here, or the Hall current, comes not, at least in this picture, and I think this is the correct one. They claim that they can also measure the currents in these stripes and see how these stripes move from the center to the border. In this picture, the currents are not carried by one-body edge states or only bulk states, but they are really carried by these mesoscopic incompressible stripes. And the mechanism there is really the one of bulk conductance in these systems. Okay, so I guess, okay, and then if you apply a voltage, these currents will become asymmetric and lead to a net current, net Hall current. Okay, good. So this was my introduction, and what I would like to do now is I would like to show you microscopic models for systems of interacting fermions, because I think for non-interacting fermions, most things are well understood, that are gapped in the bulk, and I will say precisely what I mean by this, and ask how these systems respond to perturbations. But the idea is really we want to describe electron gases, which describe which are in such an incompressible state, and understand how they respond to perturbations. So before going into math, let me give you one more picture, which is more maybe now.
Stefan, sorry to interrupt. There is a question in the audience. Yes, Kieran?
Is it known how accurate the Thomas Fermi theory is, or what inaccuracies it for these systems? Or is there
actually, I'm not sure if I can give you a satisfactory answer. So from a mathematical point of view, certainly, I mean, you will find in this paper, I mean, you see in what limit it becomes exact. And I don't know, I mean, if this magnetic Thomas Fermi theory is as well understood as the usual one, but I think at least these physicists who really describe experiments where they then also probe the location of these currents, they are not worried about the inaccuracy of the Thomas Fermi approximation. They are more worried than later on about taking into account, of course, disorder in this system, which will very easily break the symmetric picture and dissipation in these systems. But that's actually all I can say. Because I would like to really understand if in really microscopic models, we can understand these incompressible phases of fermion systems and how they respond. And why this is a non-trivial question, I would like to, before going to the math, explain in another picture. So if I draw this this idea, what I would like to understand in the situation of non-interacting fermions let's say in a homogeneous, in a crystal, then, in an insulator, we will have Bloch bands, or in a periodic system, we will have Bloch bands, so intervals of spectrum separated by gaps. And if the Fermi energy is in such a gap, and we are at 0 temperature or at very low temperature, all the states in one of these bands are occupied, and all other states are not occupied. So the question is now, how does such a system react to an external perturbation like a linear potential, okay, a constant electric field? So, and what we expect is that because of the Pauli principle, the electrons cannot rearrange within this occupied band. So actually what one expects is that basically the state of the electrons changes only very little, although, so to say, the local energy of the states will be shifted by this linear potential. And why can they, so to say, not occupy other bands? Because an electron, to go to an unoccupied state, it either has to overcome a local gap, or it has to tunnel a long distance to another energetically favorable or more favorable state. So actually the electron gas is locked in this lower band, although energetically this might not be the optimal state anymore for the system. Okay. And basically this mechanism here we would like to understand in models of interacting fermions. Okay, after this quite long introduction, let me start with the mathematical setup for the results I would like to present. So we will consider models for fermions that are on a lattice, for simplicity ZD. So we will look at so-called tight binding models. And to describe an interacting system, we have to restrict for the beginning on finite sets. So X is now the finite configuration space. Think of a cube or a square or some patch of material. Then, and I can do this quickly because all of this was explained yesterday twice by Volker and then also by Benji. So the n-particle Hilbert space for such a system is just the antisymmetric tensor product of the single particle spaces. In this case, X is a finite set, a finite configuration space, and we also assume that so to say, the local on-site Hilbert space is finite dimensional. Think of S being spin degrees of freedom or some internal lattice degrees of freedom. But this one-body space is a finite space, so also this discrete, this tensor product is a finite dimensional space, and also the corresponding Fock space is finite dimensional because the one-body space has S times volume, cardinality of X dimensions. So you cannot fit more fermions into this space than X times volume of S times volumes of X. So the nice thing about this is all the spaces are finite dimensional, so we will not be worried about domains for the moment. Okay, just to fix the notation, set up the formalism. We have the algebra of bounded operators on this Fock space over finite patch, and this is generated by the fermionic creation annihilation operators. We saw them yesterday. Now they are labeled actually by points in the set X. So we now do this in position space. They satisfy the canonical anti-commutation relations we saw yesterday. And we will denote by curly A sub X the subalgebra of those operators that commute with the number operator in that region, because we will not be interested in creation annihilation of particles. So the total number of particles will be conserved in our models. Okay, and so this is the very simple setup. That's basically only linear algebra. Everything is finite dimensional. But in the end, we would like to go to do a thermodynamic limit to also consider infinite systems of such fermions on the lattice. And to this end, we introduce the so-called algebra of local observables, which is just the union of all operators that are localized on finite patches. So this makes sense because if Y is a subset of X, then the operators localized in the region Y are actually also operators in this acting on this larger region X. And for an operator to be localized in a region X just means that it can be written as a linear combination of products of creation and annihilation operators in that region. Okay, so that's the local algebra. And then one defines the so-called quasi-local algebra, which is just the closure of this algebra of bounded operators with respect to the operator norm. Okay, and this is thought of to be the observable algebra of the infinitely extended system. And you should think here of these local observables as an analogy of compactly supported, let's say, continuous functions. And then if you take the closure with respect to the sup norm, which corresponds to the operator norm, you will get continuous functions vanishing at infinity. So these are observables which somehow are local, but not really. They might have slow decay at infinity. Okay, good. And to be more explicit about the thermodynamic limit in the following, we will look at sequences of finite systems, for example, or we will look at sequences of cubes. So we will consider our electron or fermion systems on sequences of cubes of side length 2k plus 1 in ZT. Okay, and now we would also like to set up Hamiltonians, interesting Hamiltonians for our fermionic systems. And we want to also define them on arbitrarily large cubes. So what one does is one defines these operators on a cube of size k, on a cube lambda k, in terms of so-called interactions. So an interaction, yeah, I mean, that's a technical name. Maybe it's not a really good name for this, but an interaction is the map that maps finite subsets of our lattice to local observables supported on that subset. And if we have such a map for all subsets X, then we can define a Hamiltonian supported on the cube lambda k by just summing all the local observables in the interaction over all subsets contained in the cube. And the typical interaction we would be interested in, so modeling maybe a quantum Hall system would be of that type. So we would have actually only operators that are either supported on 2 points or on 1 point. And those on 2 points might be or will be so-called hopping, so kinetic energy terms, hopping terms, and for example, density interaction terms. So W would be an interaction potential, and T would be the, so to say, the discrete kinetic energy operator. And one single side terms, the external potential or this chemical potential, which we will have to introduce. So that would be for example, if W would be only on site and this would be nearest neighbor, that, sorry, this is my mouse, which I should not use here, okay. Then we would get a Fermi-Hubbard model on the lattice. Okay, good. And we will be interested in the thermodynamic limit. And to this end, let me note that actually the norm of such an Hamiltonian, such a sum of local terms operator, will grow like the volume of lambda k. So at least in the sense of bounded operators, this object will not have a nice limit. Okay. Then this is a technical slide I would actually like to jump over just so you later on see what these symbols mean. We would like to prove theorems, to put some topology on these interactions phi in terms of their decay properties. And this is a way to define a norm on such interactions, which I'm not going to explain in detail, that decay like a certain decay function zeta. So zeta is assumed to be a rapidly decaying function. In the following, often we will assume this to be an exponential function. So actually, we will look at interacting systems, but with short-range interactions, not with Coulomb interactions. There's no way to do what I'm going to do for Coulomb systems at the moment. And we will also have to introduce spaces of quasi-local observables with certain decay properties, and they are denoted by this d zeta, and zeta is again a rapidly decaying function. And with these norms, we get Banach spaces of decaying interactions and decaying observables. Okay, good. So now this I described you some formalism. So what can one do with this? One can, for example, now look at the thermodynamic, or prove that such systems I just described do have a thermodynamic limit for the dynamics. So what does this mean? As I said, I mean, there will be no thermodynamic, there will be no Fock space for infinitely many particles, there will be no Hamiltonian for infinitely many particles, but there will be a dynamics, a time evolution on the algebra of quasi-local observables, which is just obtained by looking at the Heisenberg evolution of local observables on finite sets and taking the limit, the thermodynamic limit. So this UT defines this time evolution, a one-parameter family of algebra automorphisms of A for this infinite system. So we have an infinite system dynamics, and it has a generator, which is called the Liouvillean on the infinite system. And actually, one can add here technical details, which are maybe interesting for the mathematician in the audience. So, for example, if one looks at subsets, Banach spaces of this quasi-local algebra of observables with somewhat better decay, then one can give explicit conditions on F1 and F2 on this decay to make sure that, for example, that this time evolution maps from F1 decay to F2 decay. So these would be sort of propagation estimates in this for these observables in this infinite algebra. And one can now, for example, also show that these local Heisenberg time evolutions, these one converge really in norm to this infinite volume dynamics. And the same, similar statements one can show about the Liouvillean, the commutator on with H naught on finite sets. So this is all very well known and has a long history, which I will not try to recall. But let me just say that doing this thermodynamic limit for these kind of systems, so for these kind of lattice fermions or also lattice spin systems, all relays on so-called Lieb-Robertson bounds, which are bounds that show that actually this Heisenberg evolution of local observables spreads the support of these observables only with a finite speed. And there has been a lot of math work on this. Let me only mention that recently, and these are things we use ourselves, recent results by Jean-Bernard Bru, Walter Pedra, Bruno Nachtergaale, and co-workers, Moon Ogata, and ourselves. These were basically all results which try to get a better understanding of this uniformity of this thermodynamic limit in specific function spaces. Okay, good. But what I would like to talk now about is what I said in the beginning. We look at the system which is at a gapped system, so which starts in an incompressible state. And so let me now explain what I call the standard gap assumption for such systems. And the standard gap assumption is just the assumption that the local Hamiltonians, H and lambda k, which are matrices, have a gap above the smallest eigenvalue, the ground state energy, that is uniformly in the volume bounded away from zero. Okay, so this is the gap G. Let me mention that this is a highly non-trivial condition because if you, the dimension of our Fock space is exponential in the volume lambda k. So it's 2 to the lambda k. And the norm of this matrix here is linear in the norm in the volume of lambda k. So the typical level spacing in these systems will be exponentially small in lambda k. So it will be 2 to the minus lambda k. So you have typically exponentially small level spacing. And so the assumption that there's a gap of order 1 for all system sizes is a very strong assumption. And actually, it's not easy to check, but there are systems where one can expect such a gap and also can prove such a gap. These are, for example, electrons in a Chern trivial insulator, where the potential mu is in a band gap. So basically the situation I sketched in the picture before. Then if we look at Chern non-trivial insulators, in particular at quantum Hall systems, then actually these finite volume Hamiltonians do not have a spectral gap because, so to say, of the edges of the system. But under some conditions, one can find periodic boundary conditions where these systems are gapped again. And another example would be if we look at the discrete Dirac operator on our Dirac particles on the lattice, massive Dirac particles. The filled Dirac sea would also be such a gapped ground state for such a system. Okay. Good. So once more back to this picture. So we have this gapped ground state. So here again, this is the one-body picture or the non-interacting picture. Then the corresponding gapped ground state would just be a Slater determinant, or in the one-body space, the Fermi projection. And we expect that this Slater determinant or this Fermi projection is by adding such a for example, linear potential corresponding to a small electric field, that this state would be only very little changed. Although, no matter, now think about the infinite extended system. Yeah, think about the infinite volume system. No matter how small I make here the slope epsilon, this gap here will certainly be closed after some distance. So it's obvious basically from the picture that this state we get here by occupying still locally the lowest band will not be a ground state of the perturbed Hamiltonian. It will be, the perturbed Hamiltonian will actually have no ground state. It will have a spectrum, the whole line here. But still, physically, we expect that the system goes from this gapped ground state into such a state which is very close by to this, but not a ground state of the perturbed Hamiltonian anymore. And we call such states non-equilibrium almost stationary states, or short NEAs, because as we will see, they are really stationary or almost stationary under the dynamics of the perturbed Hamiltonian, but they do not correspond to an equilibrium state in the sense it's not a zero temperature equilibrium state, not a ground state, and also not a positive temperature global equilibrium state. Okay. And that's also the case. Okay, this is actually here the headline. What I wanted to say is this is the reason we want to characterize these states here, but we cannot characterize them as ground states of the perturbed Hamiltonian. So what we do is actually we use linear or adiabatic response. We ask ourselves, how does this system respond dynamically if we start in such a gap ground state and dynamically now turn on such a perturbation V? What does the system do dynamically? Okay, and we will turn on these perturbations adiabatically. That's why I'm talking about adiabatic response in the following. And actually, in non-interacting systems, this is very well understood, although it might have not been well known for quite some time. This adiabatic theory for what Georg Nenschu called almost invariant subspaces, because here now the ground state in the non-interacting case is a Fermi projection in the one-body picture, so it's an infinite dimensional subspace of the one-body Hilbert space. And this theory for this almost invariant subspaces was established by at least the idea was started by Nenschu long ago. and then worked out in great detail by Nenshu and Zordoni. And we picked this up and somehow formulated a more general theory of what we call space adiabatic perturbation theory at that time. Okay, good. So now, okay, I see I have to hurry up. Now I would like to present a corresponding adiabatic theorem for these interacting systems. So to this end, we will now look at the time dependent. So we want to turn on the perturbation in a time dependent fashion. At a time dependent Hamiltonian, actually the H0, maybe in applications will not time dependent, but for the math, we allow it to also depend on time. H0 will be assumed to be gapped at all times. And then there's the time dependent perturbation, which could include such a linear or Lipschitz continuous potential and some small local terms. So we have a time-dependent Hamiltonian H epsilon corresponding of a gapped part and a perturbation, which might close the gap, as I showed you. We can easily show that also in this case, in the thermodynamic limit, we will have a corresponding evolution family on the quasi-local algebra. So in this thermodynamic limit, so we again get a well-defined dynamics for the infinite system. And we do here adiabatic scaling. That means we look at the dynamics generated by 1 over eta times the Liouvillean, where eta is the adiabatic parameter. So to say that's the standard adiabatic scaling. Okay, so we have an evolution family of the infinite system. And what we would like, okay. And if we put actually epsilon to 0 here, so we have only the H0 of t, we are in the situation of the standard adiabatic theorem, which you most likely know for finite systems or for small systems. It just says if you start in a gapped eigenstate of the system and modify the Hamiltonian adiabatically, the dynamics will really follow the corresponding eigenspace as long as the gap doesn't close. And here we would have a similar statement, but for this infinitely extended fermion system. Okay, good. So, there's a question I see in the.
John Feng. Yeah.
John Feng, hi.
Hello. Just want to clarify. So when the Lipschitz potential, so is it Lipschitz in time or Lipschitz in space? So why is it needed?
No, it's Lipschitz in space, and also the time derivatives are Lipschitz in space. It's basically needed. We want the gradient. I mean, the gradient of V to be bounded. So we allow for linear potential, but not more.
I see.
Yes. Okay. Good. So let me quickly mention that actually adiabatic theorem for such extended many-body systems have been out of reach until very recently. So the first such adiabatic theorem for an extended system was proved by Sven Bachmann, Wojciech Dorek, and Martin Fraß. And they look at the case epsilon 0, so the standard setting of having a gapped ground state for time-dependent Hamiltonian. And what they do, they look at finite volume, but they were the first to be able to prove an adiabatic theorem for such systems with error estimates that are uniform in the volume. Because if you apply the standard adiabatic theorem to this setting, your error estimates would explode with the volume. So would become worthless in the thermodynamic limit. And this is actually, I think, a really nice and original mathematical work. And basically, what I'm going to tell you is based in many respects on ideas from there. Then I extended this result to the case of with these type of perturbations. So where we go from ground states to these non-equilibrium almost stationary states, but again on finite volumes. And together with a student, we basically put these things together, and these results about the thermodynamic limit I quoted before to show that one can actually lift these results here to the infinite volume description, so to the evolution of the on the quasi-local algebra. But this was just technically putting together what existed before. And the result I want to now present you in the last minutes is now an adiabatic theorem with a gap in the bulk, where we don't want to assume that these finite volume Hamiltonians are gapped. So a result that really applies also to turn non-trivial systems, even if they are far away gap edge states which close the gap. So the idea is we don't want to put things on a torus to remove the boundaries. We want to understand what happens in the bulk of a system that is only gapped in the bulk. Okay. And not globally. And to formalize this idea mathematically, in the infinite, so the idea is that we require the spectral gap only once we are on the thermodynamic limit, once we remove the boundaries to infinity. So the idea is to require the spectral gap only for the infinite system and not for the finite systems. But of course, as I said already, there's no limiting Hamiltonian for the infinite system. So one has to come up with a new characterization of what it means for a system to be gapped for such an infinite extended systems. And there's a definition for a ground state of such a Liouvillean on the quasi-local algebra of the infinite system, which I give here, which I will not detail. I just say if you look at this condition on finite volumes, it's sort of say equivalent to rho being a ground state of the Hamiltonian. Okay, and with the state on the algebra, there is associated actually a representation of this quasi-local algebra on a Hilbert space again, this so-called GNS representation. And in this GNS representation, there is a unique self-adjoint operator, H rho, the so-called GNS Hamiltonian, which generates the time evolution, which we have on our quasi-local algebra, now in this representation on this new Hilbert space. Okay, so this is an abstract, rather abstract construction, which allows you to represent your algebra on a Hilbert space, and there the evolution is again generated by a Hamiltonian, the GNS Hamiltonian. And now the definition of a gap assumption in the bulk, which was first given in a paper by Moon and Ogata, is just the assumption that this GNS Hamiltonian has a gap above its ground state. By construction, the ground state energy of this GNS Hamiltonian is always zero. So the assumption is that this infinite volume GNS Hamiltonian has a ground state gap above zero. And actually, this gap assumption includes another assumption, namely that the ground state of the infinite volume Liouvillean is unique. And that is a very strong assumption, which is not easy to check. Okay, but from a mathematical point of view, that characterizes the idea that our system is gapped, behaves like a gapped system in the bulk. And then, under these assumptions, we can prove an adiabatic theorem. So we have a time-dependent Hamiltonian of the type I showed you before, the corresponding time evolution generated on the infinite volume algebra. And then the statement is the following, that uniformly in these two small parameters, for all values of these small parameters, we can construct an automorphism of the algebra, denoted here by beta, which is near identity, which is almost the identity, and it's actually an automorphism on this quasi-local algebra. So actually, it acts locally on the state, if you like, such that if we compose the ground state rho t, the infinite volume ground state, with this near identity local automorphism, so we only make small changes locally, you should think, then we get a new state. And this is exactly this near state I tried to describe before. This is exactly this response of this incompressible ground state rho t to this external perturbations, which can act globally and which can be very large, as you saw. And it has the following, yeah?
So the standard adiabatic result looks like the form of like the norm of the derivative divided by gap, right? Roughly.
Okay, sorry, could you try to speak towards the microphone? I couldn't really understand you.
Okay, I'll try my best. So, so the standard adiabatic result takes the form of a norm of the derivative of Hamiltonian divided by gap, roughly. Does it make sense?
I mean, yes. I mean that you can find, so to say, error bounds of this form. Yeah.
Right.
The standard adiabatic theorem, actually, we would have epsilon equal to 0. And at leading order, we would just take beta equal the identity. So let me maybe formulate the statement down here, and then let me compare it to the standard adiabatic theorem.
Okay, yeah, I'll ask questions later.
Okay, good. So the statement here is that if we start in this Nea state at time 0, and then we act with this full time evolution generated by our time-dependent Hamiltonian, then and compare then with the corresponding Nea state at time t, when we test against local or quasi-local observables, then this difference is actually small if epsilon and eta are small. Okay, so see that actually this is smaller than any power of epsilon and smaller than any power of eta, because n is arbitrary, only the constant depends on n, so that's an asymptotic result. While the power here in the denominator d is just a fixed dimension, so this does not grow with n. Okay, so meaning that the evolution transports these Nea states from one time to another time. So if we put epsilon and eta equals to 0, then okay, we would not have here a result, but in the usual adiabatic theorem we would have a result. No, let's say no, we put epsilon to 0, then the result would be in the usual adiabatic theorem that the ground state at time t0 will be transported adiabatically into the ground state at time t up to errors which are of order eta. And then the constant might depend on the time derivative of the Hamiltonian or its norm and the gap and so on. Okay. So in the standard adiabatic theorem, we would transport ground states to ground states. But if you want to have better estimates here, we have to slightly modify, so to address these ground states locally.
May I ask a question? Is the left side, is this a norm rather than an absolute value?
No, this is, so to say, a state applied to an observable element of the algebra. So that's a number, and it's really the absolute value of the number.
Okay, I see.
Okay, so let me, since my time is over.
Just to follow up on the previous question. So if it were the norm of the Hamiltonian divided by gap, and gap is a constant, but the norm of the Hamiltonian is that norm of the derivative of the Hamiltonian can still grow, right? So
yes.
How to resolve this thing that allows you to pass to the thermodynamic limit?
Okay, so what you're saying is exactly the reason why you cannot use the standard adiabatic theorem. You cannot use the standard arguments, because then this bound would explode in the thermodynamic limit.
Right. So
because the norm of h and the norm of h dot would grow unless you change h only very locally so that the derivative is really bounded, but that would not be interesting.
Right.
So what you just said is exactly the reason why the standard adiabatic theorem does not apply. The constant here would explode in the thermodynamic limit.
And could you roughly point out again what is the main reason for the innovation that allows you to overcome this generic argument?
Okay, this I didn't say yet, and I didn't really plan to speak about the proof. But okay, one thing is here. In which sense do we now compare the states? We test against quasi-local observables. So we test only locally the difference. And in the standard adiabatic theorem, we would look at the norm of the difference of the states. Okay, so that's basically what we do differently here. We cannot, if we compare now the norm of these states, let's say we go to finite but large volume, then these are just these are just rank 1 projections, and we would compare the norm of the difference that would not be small in the thermodynamic limit. It's only small because we look locally. So the whole thing is based on this idea that these systems react and change locally to perturbations. And that's, no matter how large the system is, if we look locally, the adiabatic theorem still holds.
Is this still based on some manipulating the resolvent applied to these local things?
Okay, now maybe I can say something in the break. I'm afraid that I prepared some slides, but I think that will be too long. Maybe I can say this in the question session. Let me just very briefly conclude with the talk. I'm almost through. I mean, there are some properties one could mention. The only property I would like to mention is that actually these states here, in particular, if you put eta to 0, so the idea is we turn on such a perturbation and then we look at the static situation again. These states have a very explicit asymptotic expansion in powers of epsilon. So we can really compute what these states are. We can compute how the ground state changes. And as a consequence, the question is, why is this useful? I mean, this is very abstract stuff. Can one do anything useful with it? And the answer, I would say, is yes, because it provides a way to prove actually to justify the usual linear response or even higher order response computations you do in these kind of systems. It tells you that linear response computations, if you start in an initially gapped ground state, so if you start in an incompressible state, then you can do linear response. Perturbatively, you can do the usual computations you would do naively, and they give you indeed the right response coefficients. We discussed this application, for example, in a paper with Joscha Henhaik. Okay, I think I can just skip this here, and it's sort of okay. And thank you. I mean, I listed here the reference only because I was asked to also provide the slides. So if anybody is interested in the references, you will find them in the slides online. And with this, I would like to close and thank you very much for your extended attention and the many good questions.